Hello everyone, and welcome back to Electronics Prepper, the channel where we try to learn as much as possible about electronics to become more self-reliant with technology and prepared for the future. Today I would like to show you a relatively small but very useful, very versatile circuit that we may need sometimes when we are working with transistors on the so-called high side, on the positive side, and we need to turn them on. And for that, we need an extra voltage on top of whatever voltage we have. There are various tricks that we could use, typically called bootstrap techniques. However, sometimes we just cannot use such techniques. So we just need to have an extra voltage for polarization, or sometimes called bias in English. And well, if we only have one power supply or one voltage, then we just need to generate this extra voltage somehow. In other words, we need a very primitive DC-DC step-up converter. Of course, we could just use a DC-DC converter from the market or design one of our own with integrated circuits that are specialized for this kind of application. But in order to just have a few milliamps of current, this doesn't make all that much sense. We could use something relatively small, simple, and preferably without integrated circuits. This is what I will show you in this video. In order to better understand the problem, let me present the problem to you in a visual way. So let's say we have a circuit that has one voltage, okay, so one power supply, whatever that may be, battery, accumulator, dedicated power supply, it doesn't matter. And we want to turn on and off this voltage, maybe even adjust this voltage for the output. And we might decide to use an N-channel MOSFET, even though we could just as easily use an NPN bipolar transistor. The problem is the same, it's just that with N-channel MOSFETs, this problem is much bigger than with NPN transistors. So we have the so-called pass transistor, an N-channel MOSFET, and in order to turn this MOSFET on, so if this, as we know by now, this is the drain, this is the source, and this is the gate, pardon my not so pretty writing here. In order to turn on N-channel MOSFET on, especially if you want to turn him on completely, then we need to apply a gate to source voltage, okay, that it's anywhere between 5 and, in extreme cases, 15 volts. Of course, depends on what current we want to pass through him and all sorts of other factors. Now, when he turns on, for all practical purposes, it's like he's making a short circuit between the drain and the source. Almost, not quite, but you know, ideally this resistance, drain to source resistance, when he's turned on, should be as small as possible, so we could consider this resistance 0 for the purpose of this video. When this resistor is 0 or close to 0, whatever voltage we want to have on the output is essentially the same voltage on the input, meaning the same potential is found on the drain as on the source. So now, if we are to turn this transistor on, we need to apply a gate to source voltage that is bigger than the input voltage, okay? And this is where the problem lies, because we don't have anything bigger. This problem becomes even more acute when the input voltage is around, it has a relatively small value and is around the same voltage as the turn-on voltage of the transistor. So let's say the input voltage is 5 volts, which can be very common, especially if we want to turn on and off logic circuits later. Well, for most parts, in most cases, we need to have a gate to source voltage of also approximately 5 volts. This means that on the output we will pretty much not have anything if we just connect the gate to this positive voltage On the output, we will have a very small voltage, if anything. We need to drag this gate up to a higher potential, okay? If we would have an extra voltage here, then this would be possible, especially if the voltage would be high enough. However, like I said, in this video I'm presenting to you a circuit that generates this extra voltage for the times that we just don't have this extra voltage coming from the previous stages of our circuits, okay? So this is why this circuit is useful. And like I said, I wanted to design, recently I needed to create the video that I showed earlier with a very simple lithium-ion, lithium-iron phosphate accumulator charger that can be powered from 5 volts, and I needed to use an N-channel MOSFET, so I needed to design this a circuit that would generate this extra voltage so that I don't have to bother with anything else. And well, in this case, in the case of this simple charger, you know, there are other possibilities that are available to us. Like I showed in the previous video, we can just use a computer power supply that gives also 12 volts besides 5. However, in other cases, in other situations, we might not have this extra voltage. I wanted a circuit that is simple to understand, simple to create, does not require an integrated circuit, so here he is. This is what I will show you in this video. I will go step by step in the functioning of the circuit, how and what happens here, so that you can easily understand and implement this in your own circuits, in your own projects. Before we dive deeper, please allow me to thank the sponsor of this video, which is PCBWay. PCBWay is a leading PCB manufacturer that can help you build your dream projects, no matter how advanced they are. They can create just the PCBs for you or help you as well solder components on them through PCB assembly services. If you're creating a full device, they can help you create a plastic case through either 3D printing or injection molding services, or even CNC machining if you need custom metal pieces for a metallic case. You're free to use your favorite design software, upload the Gerber files, and one of their professional representatives will contact you, offering you one-on-one customer service. All you need to do is go to PCBWay.com, the link is in the description. Thank you very much, PCBWay, for sponsoring this video. And now let's get deep into today's circuit and see how he works. We have only 4 transistors, of course, a coil, an inductor, right, and a few other passive components around. And that's it. That's all we need to generate this extra voltage. That's all we need to create this simple step-up converter. No ICs necessary, no super complex calculations, no nothing. I'm gonna have to draw various things, so let me make a print screen of this schematic and let's start. So, as we see, we have a single voltage on the input. This can be from 3 volts upwards. For very, very low loads on the output, we can go even lower than 3 volts on the input. However, I cannot guarantee that the circuit will be stable under 3 volts. The upper voltage is strictly dictated by the maximum drain to source voltage of the MOSFET used and the maximum collector emitter voltage of the transistors used, of the bipolar transistors used here. Okay, there's no other limiting factor. And of course, we will have to use, you know, good enough capacitor for the output, depending on whatever voltage we need to have. But other than that, there's no limit to how much we can go upwards. So we have, since we need to generate an extra voltage, we need to essentially employ the same principle that any step-up converter uses, which is push a current down an inductor or a coil of any kind in one phase, and in the next phase this inductor will transform into current source, and we want this current source to be in series with the current that the power supply, the input power supply, is delivering. Okay, so this is essentially what happens like in any other step-up converters. We have this inductor here, a couple of resistors that I will mention in a moment, their role, and a switching transistor, which in my case it's a 2N7000 N-channel MOSFET. This model can be found easily on the market. He's cheap, he's found in abundance, so absolutely no problem whatsoever. This MOSFET is turned on, it's polarized through R5 resistor, and he gets to be turned on with a slight delay due to capacitor 2. I will get into a moment to this delay and why he's needed. He's not needed initially for the first impulse, he's needed afterwards. So basically we apply the input voltage, okay? This voltage will generate a current through here and apply voltage to the gate and the source of the MOSFET, which at some point in time will turn on. When he will turn on, and let me make a small graphic with time on the x-axis and the current on the y-axis. When this MOSFET will be turned on, current will start to flow through the inductor. And as we know, current through an inductor does not flow immediately to the maximum value, but actually starts to ramp up over time in a more or less linear fashion. This is something that we want to happen, of course, because we need to charge with energy this inductor, okay? Now, we need to stop this current from going over a certain limit, and in my case it was 200 milliamps, which is the maximum drain current of this model of MOSFET transistor. So in order to monitor the current, we are using two shunt resistors. We could have used a single resistor, but I needed to have a 3 ohm resistor, and 3 ohms is not exactly a standard value, at least not as far as simple resistors are concerned. So I use 1.2 in series with 1.8 to have my 3 ohm resistance. Okay. Why 3 ohms? Because when I have 200 milliamps of current flowing through here, and obviously that's the same current flowing through the inductor, I want to open a transistor, which is transistor 2 over here, an PNP transistor. Doesn't really matter the model, I chose BC557, but it really does not matter all that much. All it matters is that it's a silicon transistor, not a germanium one. So when we have 200 milliamps going through 3 ohms, that's 600 millivolts, and that's the good enough voltage to open this PNP transistor, okay? Which in turn will open himself, will drag will drag his collector upwards, which is connected through resistor 7 to the base of this transistor 4 over here. And essentially will open this transistor 4. This transistor 4, it's an NPN bipolar transistor with emitter connected to the ground and collector to the gate of the MOSFET. When he will turn on, he will essentially short circuit the gate to the ground, turning off the MOSFET. Okay, and this is what we want. We want this MOSFET to be turned off when this maximum current has reached. And that's basically the first phase of this entire cycle that we are describing here, okay? So now we have a certain maximum current flowing through the inductor, we turn off the MOSFET, and the inductor will start to generate, we will want to, keep the current going in the same direction, so he will generate a voltage across him that will be essentially in series with the input voltage. Okay, we'll have positive here, negative here, and we'll try to push a current in the same direction. Now, this current cannot flow through pretty much anything. Sure, a very small value will go for a very small amount of time, will go through this transistor and through these two resistors down to the ground, but this transistor too will be turned off pretty quickly once the current will start to decrease, so not much current will flow through here. However, most of the current will go through this diode, this Schottky diode, which is placed in this particular way, and will go in mostly into this capacitor here, which is connected with the negative pole on the positive of the input voltage, and the positive it's connected to this diode. So essentially, when this coil will generate her own current, this current will charge this capacitor up until a certain point. Now, if he doesn't get charged enough to open transistor 1, then the whole cycle will repeat pretty soon. However, if the voltage, when the voltage on capacitor 1 becomes high enough, transistor 1 will open and basically will function similarly with transistor 2. By him opening himself, he will pull up the base of transistor 4, which will turn on and remain turned on for as long as the voltage here doesn't drop, okay, to a certain threshold. And essentially, we will not have a new pulse going through the inductor while this voltage remains above a certain threshold. When this voltage, however, drops below the threshold dictated by resistor 1 and 2, because these are voltage dividers that dictate the emitter base voltage of transistor 1, and therefore when he will be opened and stay opened. When this voltage drops too much and transistor 1 turns off, transistor 4 will be able to also turn off. He is helped to turn off a little bit faster than how he would naturally by this resistor 8 over here, determined experimentally to be around 75K. And when this transistor 4 will turn off, then capacitor 2 will be able to slowly charge up again, okay, because resistor 2 is constantly providing current here. And at a little bit later point in time, transistor 3, the MOSFET, will be able to turn on again, generate, so the current goes down in all of this time, and then the transistor 3 turns on again at a later point in time, will also make the current ramp up, and when the current reaches 0.6 volts across emitter base of transistor 2, he will turn on, which in turn turns on again transistor 4, which turns off the MOSFET. The coil injects a new impulse of current through the diode into the capacitor. This will also turn on the transistor 1 again, which will maintain transistor 4 turned on, which makes sure that a new impulse is not generated by the MOSFET too early, and so on and so forth. So the cycle keeps repeating, and the nice thing about this circuit is that we don't have a fixed frequency. We don't need to concern ourselves with whether we're in continuous mode, in discontinuous mode. None of that matters. The circuit himself will turn on when needed, turn off when needed, and stay turned off as long as there's no need to generate new currents, new voltage impulses, okay? I have determined experimentally that it is needed, capacitor 2 is needed to be around 150 picofarads. Higher values work, but then the impulses will be farther apart, and overall we won't be able to generate enough milliamps of current on the output. So I have determined experimentally that 150 picofarad seems to be good enough. A too small value will tend to make the circuit not oscillate anymore, and we do not want the circuit to remain stable in a certain position. We want him to oscillate, okay? And that's, well, that's pretty much it in terms of how this works, and you know, how to calculate components values. For these currents here that turn on transistor 4, I wanted them to be around 1 milliamp or so. This is why I chose 18 kilo ohms here, because from the ground up to the output point, which is here, we have, give or take, 17 or 18 volts. So divided by 18 kilo ohms, that's 1 milliamp. Okay. More or less something similar is here with this 1 kilo ohm resistor. This 12 kilo is also chosen more or less arbitrarily. However, resistor 5 and capacitor 2 essentially form an RC network that has a certain time constant. So if we are to decrease the value of R5, we would need to increase the value of capacitor 2 and vice versa. And also resistors 1 and 2, these need to be as high as possible, because these resistors will essentially discharge capacitor 1, which needs to stay charged as much as possible. We don't need super high currents on transistor 1, so obviously in the base of him we want as small currents as possible. Therefore, these two resistors should be as high as possible. I chose 5.6 kilo ohms and 120 kilo ohms here. The idea is that the output voltage is dictated by these two resistors, okay? Because in order to have 0.6 volts across here, right, obviously we need to have proportionally more from here to here due to this resistor. I would suggest that you just keep 5.6K resistor between the emitter and the base, and just adjust resistor 2 to be smaller or higher depending on what voltage you want to have on the output. If you want higher voltages, then of course you need to increase the resistor 2. If you want to have smaller voltages, you decrease resistor 2, okay? These two values here give me about 13 volts from the output to the positive rail, okay? So this voltage here. Why? Because, well, if we have 120 divided by 125.6, the sum of them, and multiply that by we have 125.6 total resistance divided by 5.6 the resistance only across a base emitter. Multiply that by 0.6 volts approximately, the turning on voltage of the PNP transistor, and we get about 13.5 volts, which is something that we will see shortly when we go to the workbench, because I want to show you this practically. Okay. Capacitor 1 needs to be as high as possible. However, don't make him too big. Don't make him way too big, because then he will have a problem getting charged. I've seen that 10 microfarads seems to be nice enough. The biggest requirement is for this inductor to be around 10 millihenries. Now, I realize this sounds like a lot. Doesn't have to be 10 millihenries spot on. Can be 8, can be 7. Don't go below, I don't know, below 6. I would say it's not recommended. This won't work. It's not all that difficult to create your own inductor that has around 10 millihenries, and I will show you in a moment how two of my inductors look like. Because I used some simple ferrite cores from the ones that are used to filter out radio frequency noise on various cables, and with just a few tens of wire turns on them, I was easily able to get around 10 millihenries. So this is not all that big of a deal. Also, there are around 10 millihenries inductors found on the market that you can just go ahead and buy. This diode also needs to be, for the most part, needs to be a Schottky diode, cannot be a rectifier diode, because whenever we have some significant current drawn from the output, we will have quite frequent impulses that this circuit will generate, and frequent impulses means high frequency. Therefore, at some point, a regular rectifier diode will not be able to work anymore. So this is why we need a Schottky diode. And this is pretty much it in terms of how this circuit works. Let me quickly show you, where is that? MicroCap simulation. Okay, I have created the circuit. It's just that he's drawn a little bit different, but it's the same circuit essentially. And also on the output, I have created the circuit that needs to be connected to this higher voltage. So we have this N-channel MOSFET that we want to turn on and off through this with the help of this higher voltage. Okay, we have a push-pull configuration here connected from the ground to this higher voltage, and we have here a signal generator that turns on and off another bipolar transistor that switches this push-pull configuration, and essentially here we have impulses. Based on what frequency we use here, we will have a higher or lower current draw. Okay, let me simulate with 100 kilohertz frequency and show you how this works. With green, we see the output voltage. Okay, on the input, I have 5 volts. And on the output, we see that we got around 13-ish volts. The output voltage is not super stable, but we don't care about that. Okay, so 5 volts on the input, right? We have this MOSFET, IRFP 260, which is one of the worst in terms of input capacitance. The input capacitance of the MOSFET will be the biggest problem in terms of this circuit providing enough current to the MOSFET and the maximum voltage that will be able to be maintained. Okay, so when we have a single of this MOSFET that we want to turn on and off at 100 kilohertz, then we will have about 13 volts in total. Normally we should have had 13 volts above the input 5 volts, so a total of 18 volts. But again, because of this very nasty MOSFET, we're not able to get there, but we are able to go high enough so that we can turn him on completely. If I am to replace him with another MOSFET that is much friendlier, has a much smaller input capacitance, such as IRFS 710, then we see a completely different story. Okay, we see the output voltage jump up to almost 18 volts, remain there pretty constant, even though we are switching this MOSFET on and off at 100 kilohertz. Okay. Also, if we are to return to this nasty MOSFET, but reduce the frequency of the switching signal to just 50 kilohertz. Okay, so let's see, 50 kilohertz. Then the voltage is able to go higher than 15 volts. Okay, and yeah. Now, the problem is not all that big, because even with this very difficult MOSFET, it's enough to provide only 5 volts for him to be turned on almost to the maximum, and the resistance, the drain to source resistance, is not going to be problematic, you know. Ideally we want to have 10 volts or more, but practically we can have as low as 5 or 6 volts without a problem. Yeah, so this is it. I will put both this MicroCap circuit schematic and the KiCad circuit on Patreon to be able to download this, so that you don't have to redraw this. Now let's go to the workbench and see in practice how this works. So I will use an adjustable power source on the input. I'm going from 3 volts upwards to whatever, and I'm going to put you know, a probe initially on the input and output points, and at some point I'm going to put one of the probes here in this switching node where the anode of the Schottky diode connects to the inductor. So I will show you the impulses that this circuit generates. Okay, so you can clearly see how this works. So just allow me one moment to go to the workbench, and please excuse the less than good sound that you're going to hear, because I have a bit of a problem with the microphone over there, so I need to drag this microphone over and speak from a distance. All right, so the idea is as follows. Okay, I'm going to take this camera and I'm going to show you the circuit. Not much to say, not much to show. I've used a perforated board because it was just easier for me. And this is a coil, handmade, right, with one of those ring cores used to eliminate radio frequency interference on cables typically. And I've also created myself another coil with another core, another ferrite core like that. For 10 millihenries, we need indeed to give quite a few turns, but it's not impossible to create such an inductor manually. It's quite doable. Okay, so I have the ground. Let me see where my finger is. I have the ground, I have the input and the output, and initially I have both channels placed here on the input and output. Okay, and I will show you. Okay, so yellow is on the input and blue is on the output. So right now I have 5 volts on the input, as we can see here, 5 volts RMS, and on the output about 17 volts, so 12 volts more. I have no load whatsoever, but I can guarantee that this circuit will work with a load, as I've shown you in the simulations. So let me turn up the input voltage, and as we can see, the output voltage tends to track pretty well the input. Okay, now I'm at the maximum of my power supply. Let me switch, and okay, so we keep going up. Input 15, output around 27, and so on and so forth. Okay, input 20, output 30 something, and we could just keep going on. Okay, going down, this can work with as low as 2 volts. Let me make this 1 volt per division. Okay, now it's a bit easier. So now I have 3 volts on the input, okay, and about 15 volts on the output. Put the measurements back. And 3 volts on the input is pretty much the minimum whenever we have output load, okay? Without a load, the circuit tends to work even with just 2 volts, but realistically speaking, we will never find ourselves with such a low voltage on the input requiring, 12 or 13 volts more, and yeah, that's never gonna be a thing. Just make sure that the voltage never drops below a certain point, because then the circuit does not oscillate anymore and remain stuck in a way that could just have the MOSFET turned on continuously and have a current that we just don't want to have going through the MOSFET, through the coil, potentially over time burning the MOSFET. So we need to have a certain minimum voltage. However, theoretically that shouldn't be a problem. Okay, now I'm going to go back to 5 volts for both channels. And I'm going to put, let me see, the yellow channel, I'm going to put him on the anode of the Schottky diode. Okay, and I'm going to show you, of course I'm going to zoom, I'm going to show you the impulses. Okay, the idea is that the circuit switches from continuous to discontinuous to just pulse based working mode naturally, without having any integrated circuits whatsoever. Okay, so I have 5 volts on the input. Okay, and I'm going to let's see, I'm going to decrease this at around 3 volts. As we can see, whenever we have 0 volts here on the switching node, we are charging the coil, the inductor. Okay, and of course, the lower the input voltage, the more time we need to charge the inductor. As we increase the input voltage, and of course the output voltage will also increase, this time decreases. And this is why we see we have more impulses per time unit, because the zero voltage time decreases, because the coil will reach maximum current faster. Okay, and we can just keep going up and up, and at some point I'm at 9 volts on the input. Okay, this circuit will naturally generate only a few impulses. Okay, the output voltage will go up to a certain level and then will drop very slowly, and during all this time the circuit will keep the MOSFET turned off, because he doesn't need to generate new impulses. And this is what we see right here. And I'm increasing the input voltage, and we see that this keeps happening. This discontinuous impulse based, I don't know how to call this this mode of functioning, okay, just occurs naturally. Okay, so we see here I don't know, 1 2 3 4 5 6 7 8 9 10 11 impulses, and then circuit stops, okay, and allows the output voltage to drop. Let me make the output voltage AC and 200 millivolts per division. Okay, so we see about 400 millivolts from the minimum to the maximum. This is how this looks like. Okay, so yeah, that's pretty much it. Let me get back, choose DC again. And now, of course, if I decrease the input voltage at some point, the circuit will naturally switch back to continuously generating impulses. That's what's gonna be needed. Okay, now we start to have more and more impulses in each group. And at some point, bang, at about 4.5 volts, the circuit naturally switched to multiple continuous impulses. And that's pretty much it in terms of how he works. So I hope you enjoyed. I hope now you know how to create such a circuit. Very useful when we want to turn on and off high side transistors, especially MOSFETs. So I will definitely use this more in my projects whenever I will need to. Let me switch back to the desktop. Okay, like I said, I will put on Patreon this schematic and the MicroCap schematic simulation so you can enjoy. This is nice because this is simple, only uses simple components that we can recover very easily. We can use, recovered resistors, recovered capacitors, any bipolar transistors whatsoever, and pretty much any MOSFET whatsoever. And we can easily recover MOSFETs from, I don't know, computer motherboards or whatever. The coil is also easy to hand manufacture. So yeah, very versatile, very useful circuit to develop more complex circuits that need an extra voltage. So thank you very much for watching. I hope you've enjoyed. Thank you very much to my Patreons supporting this project. Link to Patreon is in the description. Otherwise, you can help the channel by liking this video and hitting the subscribe button so that the YouTube algorithm can recommend my videos to other people who might be interested. Thank you very much, and I will see you soon in my next video. Bye bye.